Thank you so much for having me here today. I really appreciate this opportunity. Normally, I'd start in with a whole bunch of statistics about how the Arctic is changing, how the weather is changing, our sea level, and what the Navy's going to do about it. I'm actually going to do something just a little bit different today. I'm going to tell you a story about how I ended up where I am today, and also how I've kind of gone on a journey here from being a pretty hardcore skeptic about climate change to one who believes this is one of the preeminent challenges of our century today. So if you want, in a nutshell, you can call this the Reformed Smoker Brief, if you will. So meanwhile, what's going on? Well, this whole climate debate is going on. And frankly, I'm listening to it, but it's not all that interesting to me. First, it's like, people talking about 1 or 2 degrees. And it's like, well, shoot, I mean, you go up and down 30 degrees in a day. How much can that be? They're talking about all these computer models. Now, I've been doing this weather stuff since I was like yay high. I have lived and died by those weather models. More died than lived, especially in the early days. I know how many snowstorms those things predicted in Penn State and how many we got. And that was at like day 3. So how are you going to tell me that this forecasted 100 years, how can you do that? Come on, guys, let's get real. And then, very frankly, there was like kind of this political overtone to this, and I just wanted nothing of that. But the evidence kind of kept mounting, and as this gentleman here, Winston Churchill, once said that, sometimes we stumble across the truth, but most of the time then we just pick ourselves up and carry on as though nothing had ever happened. So I thought, well, maybe since I've kind of tripped over some things here, maybe I should at least take another look at this. So what did I see? I saw that science had really progressed, like since the time I got out of college to the time, this is like 2005, 6, 7, the science had really progressed. The computer models had progressed. The Navy had sent me to the postgraduate school in Monterey a couple times, I guess to try to get it right, get a couple more degrees. And I started to understand like the difference between the weather, which is forced by kind of what you start with, or the fancy term would be the initial conditions, and the climate, which is forced by those long-term things, like what the sun is doing, what the ocean's doing, and you could call that the boundary conditions. And you shouldn't, just because you have some issues with one on the short term, doesn't mean you can't figure out the other one on the long term. And then you look at the evidence. You just started looking at the changes, especially up in the Arctic. Somehow you had to convince yourself if there wasn't something going on, then how did you explain all the changes that were being observed? Not just forecast, but actually being observed. Well, I wasn't going to use religion, but this is pretty close here. The good news is I will not give you a test at the end, but this is the radiative transfer equation. It's the radiative transfer equation. Why do I put that up there? I put that up there because it describes the basic and physics that have been known for 100+ years as to how the sun and our Earth, or any planet, you can use this on Venus, you can use this on Mars, it works, and the atmosphere all interact. So this kind of starts saying, hey, what's going on here? So, I mean, the first and the most obvious thing to look at is, well, is the sun changing? Because is the orbit changing? I mean, we know for a fact that the Arctic, like 55 million years ago, was a subtropical forest. That's way, way, way warmer than anyone's talking about now. So like, hey, Titley, why are you getting all wound up about this stuff? Well, what you look at is, hey, the orbit of the Earth is actually different. It's not exactly round. It kind of wobbles, and then the Earth kind of does this. And you add it all up, and what happens is you get a different amount of sunlight coming in, and that small difference makes a big, big difference to the climate. But we can look back over the last 50, 100, 150 years, and we're pretty darn confident that basically we know the orbit's the same. We know the sun hasn't been appreciably changing, like plus or minus 0.1%. Okay? That's not enough to explain the changes. You look at aerosols. What's aerosols? These are little tiny particles that can like kind of stay in the atmosphere. What are they doing? Well, actually, because we've got the Clean Air Act and some stuff like that, we've actually taken them out. that actually, believe it or not, contributes to warming. Who would have thunk? This is like no good deed goes unpunished, right? But it doesn't explain maybe a quarter of the warming. That's about it, at the most, at the most. So you look at volcanoes. You know, we know volcanoes absolutely can and do cool the atmosphere. But you look over the last 150 years or so, and yeah, we've had some big ones, Krakatoa, Pinatubo, Mount St. Helens, but it's been nothing out of the ordinary and nothing that explains what the data are showing. So it sort of gets you now down into greenhouse gases. And what's the one that's been changing? It's been carbon dioxide. Well, is it natural or man-made? We can actually tell that because there's these things called these isotopes that decay at different rates. And it turns out that the ones from the dinosaurs, people don't like it when it's dinosaurs because it's really, really old plant matter, but I call it the dinosaurs and the critters. When you put that back in the atmosphere, it's a different chemical composition, and we can measure that. And we see that of the CO2 coming in the air now, it's more and more is the ones without the isotope, which means it's old carbon dioxide that we're putting back in, or old carbon we're putting back into the air there. So, but it's just a small, small, small amount. It's a trace. In fact, you got to have carbon dioxide if you want plants. We kind of like plants because we like to eat the plants, and sometimes we like to eat the animals that eat the plants. So it's not like anybody's advocating for, hey, let's get rid of all CO2. That would be a very, very bad world. It would be cold and no plants would live. So carbon dioxide is really, really useful, even though it is only a trace. But what it turns out to be, in addition to being a trace gas, is very, very effective at changing the atmosphere behavior. And people say, come on, Titley, it's just so small, it can't possibly matter. Well, let me give you another example of something that's really small. Now, these lady and Jen here on my right, your left there, how much fun does it look like they're having? Yeah, okay, maybe it's been another day in the Pentagon for them. I'm not sure, I don't know. But that doesn't look like they're having a lot of fun there. And that's why I would call that like a blood alcohol content of, what do you think? 0, okay? That's like blood alcohol content of 0. Now, let's change that here. And let's look at what maybe 0.04 looks like. Well, hey, guess what, guys? It just turns out that 0.04 is like 390, 387 parts per million, which is exactly today where we are with CO2. Now, do those folks look like they're having fun? Yeah, probably a little bit more. It's just a trace. How can a trace make a difference? Which ones do you want to party with? I'll just leave you with that. Okay, fast forward to May of 2009, my boss here, pictured here, Admiral Gary Roughhead, asked me to come be the oceanographer of his Navy, and also asked me to start looking at climate change. Now, as I mentioned, I'd done the forecast for individual ships and like bigger operations, but now what my boss is asking me to do is like, hey, Titley, come forecast for decades ahead and for the entire Navy. And it's like, no pressure there. So, but that's the challenge. That's what we need to do to really make sure that we get this right for our Navy.